we talk about symmetries? Because symmetries appear all around us. For example, in nature, I'm sure you can recognize a mirror symmetry there in the butterfly, then a rotational symmetry. For the DNA molecule, actually, we have a helical symmetry, which is a rotational symmetry combined with a translation along the rotation axis. And then maybe a less popular symmetry is a scale symmetry. There you have a coast. A coast is considered a scale symmetry because no matter the distance from which you look at it, the object will appear the same, and the intrinsic characteristics of the object will be preserved. After that, in the man-made objects, we again have the same kind of symmetries. For example, mirror symmetries, rotation. There we have a quadrilateral symmetry, which is a symmetry where we reflect with respect to two axes. And we must not think that symmetries are specific only to the visual world. They can appear, for example, also in music. So when you listen Moonlight by Beethoven, you can identify a translation symmetry at the beginning. Or there we have a glide reflection, which is a translation combined with a reflection with respect to horizontal axis. So symmetries appear everywhere. And obviously, they will appear in images and 3D shapes. Symmetries appear everywhere. And several psychophysical studies have shown that, that humans are better at recognizing objects when the objects are symmetric. So the question that I would like to look at today is, how do automatic methods work when we have symmetries? Do they work better or not? So next, I will have a look at some aspects about symmetries in images, then symmetries in 3D shapes. And in these two parts, I will briefly mention some recent works that we've done on these topics. And then I will try to put all together in a possible application. OK, so for the object recognition in images, some recent survey papers have shown that if we take into account the symmetry, then the recognition rate actually improves. So we should use symmetries. But if we look at state-of-the-art methods for object recognition in images, they are mostly based on some bag-of-words approaches, like the one that Thomas presented the other day, which use some SIFT-like descriptors which encode appearance information, but there is no clue of symmetry. And there are very few recent works that try to include the symmetry information. So why is that? Why, since it's useful, why don't we use the symmetry information? Well, because symmetry detection in images actually is a difficult task. And there are several reasons for this. And mainly, when we are given an image like this, a natural image, we have the background clutter. So we are not looking for a global symmetry. We have to look at a local level. Here we have a butterfly. At the local level, it's symmetric, but the entire image is not symmetric, so I cannot apply like a nice method like a Fourier transform or something that would point exactly to where the symmetric object is. Then another aspect is that we have to look for partial symmetries. So to us, this butterfly looks symmetric, but if you look at a pixel level, then it's not that symmetric. The values are not symmetric. So we have to be tolerant with respect to this. And then it's not the case here, but we often have also the perspective effect, which induces occlusions, and then the problem is really difficult. So what we did, we proposed a symmetry detection method that controls the number of false positives, because this is the main issue. We have a lot of false detections in the current, in the existing works. So this was a joint work with Rafael Grom Max Ovzhanikov from Polytechnic, and it was presented in a symmetry competition workshop this year at CVPR. And our method got the best accuracy on a dedicated benchmark. So our method deals with mirror symmetries. When I'm given an image like this one, we report a bounding box showing where the symmetric object is, and this is common in symmetry detection works to represent the symmetric objects through bounding boxes. We assume an orthogonal view of the objects, no perspective skew, so this is a limitation. And the main difference with respect to existing works is that we consider the detection as a two-stage process. So first we have a candidate selection, and then we add a principal validation. Most of the existing works, they only do this candidate selection. They have a heuristic, and they find some potential candidates for symmetry, but then they stop there, or they impose a threshold, and they say, okay, if my candidate was voted by, or I don't know, they have some very non-principal methods to decide where you actually have a symmetry and where you don't have. So our main concern was to diminish the false detections, and to this end we used, for the validation part, we used an a contrario approach, and I'll get back to that. Okay, so for the candidate selection, into details how we did it because I don't have time. But it's important to say that, okay, in the candidate selection, I need a method that says, okay, here you might have a candidate, here you might have a candidate. So there's no problem if it gives me too many candidates or false candidates, because I will eliminate them at the validation stage. What is important here is not to miss candidates, so not to have false negatives. Well, the safest approach would be to do an exhaustive search, but this is not feasible. So we use a voting scheme. I don't go into details here. Just to say, we use a voting scheme based on SIF features, and this gives me candidates. So now for the validation part, here is our main contribution. I'm given a patch in an image, and I try to decide if it's meaningful, if it's a meaningful symmetry or not. And in this part, in the validation part, it's important to eliminate the false positives. So to this end, we first introduce a measure of symmetry of a patch, which is based on the gradient orientation error. So this is important because the existing works, they usually look at some sift points, so at the sparse information in the image. But from our work, it seems that it's important to look at the actual image data, so to look at not only at sparse points. So what we do is we take every pair in the patch and we measure the gradient orientation error. So like in this case, I have a pixel, I compute its ideal mirror version, and then I take the error. And we sum this over the patch, and I get a degree of symmetry. Obviously, if when I sum this up, if I have a perfectly symmetric patch, then this score will be 0. If I have a very bad patch, then this score will equal the number of pairs that I have in the patch. And now what we need is to put a detection threshold on this score. And for this, we use the contrario theory, which was proposed by Jean-Michel Morel group from ENS Cachan. And their goal, their goal was to propose a statistical framework that would allow us to design detection algorithms that don't depend on parameters. Because this is a critical problem actually in detection problems, that we have to fix some parameters. We have to fix the detection thresholds, and these thresholds will have to be tuned every time we change the image. So this is a critical problem. So they propose this method, which has statistical grounds, so that we don't have to do this tuning anymore. And how do we use the non-accidentalness principle, which says that we see nothing in noise. So there should be no perception in noise. This might sound trivial, but it's not. So when I'm given an image of noise, if I apply a method, a detection method on it, it should report no detection. So to do this, we need two ingredients. First, we need to define a random model. And then, when I'm given a candidate that I try to validate, I have to answer the question, is this candidate likely to occur in the noise model, or it's an outlier? And if it's an outlier, then it means it's a structured candidate, and it should be accepted as a meaningful detection. Since for the symmetry of the patch we are looking at the gradient orientation error, a good model for the random model is a Gaussian white noise model, because it can be shown that the gradient orientations are independent and uniformly distributed random variables. So, and then to decide if a candidate is an outlier or not with respect to this model, we have to compute the p-value of the candidate, which is the probability of observing in the random model a candidate that is at least as good as my candidate. And obviously, if this probability is very small, then the candidate should be accepted. In order to impose a threshold, but in order to have a robust method, we have to consider that in an image we won't have a single candidate, but we will have several candidates. So we have to first multiply this probability by the number of candidates and then to impose a threshold. And in fact, the probability multiplied by the number of candidates gives us the expected number of candidates that are at least as good as my candidate in a noise image. And a good threshold to bound this probability, this expectation, is epsilon equals to 1. It's a simple value. And in the same time, it will allow us to deal with those imperfections that I mentioned earlier. Okay, so just to check our model, we first ran tests on noise images. So we have no detection on noise images, whereas existing algorithms, they do report detections. Sorry. And then other examples where our method prunes out successfully the false detections. Here we have multiple detections. Okay, so the question that we looked in this first part of the talk is symmetry information useful and used in object recognition in images? And the answer is yes, it's useful, but it's not. But the use is limited for now. And what we method that controls the false positives. As I said, the current limitation is that we don't handle the perspective skew. And as future work, we have to design symmetry descriptors and include them in the object recognition tasks. Okay. So this is for the images. Let's see what happens for the 3D shapes. And we are looking at the problem of finding isometric correspondences between shapes with intrinsic symmetries. So an isometry preserves geodesic distance. So if I have the distance between my finger and my shoulder, the geodesic distance is the distance that follows the surface, as opposed to the Euclidean distance that takes the shortest path. We consider isometries because they approximate well-articulated motion of humans and animals. Intrinsic symmetry. In this case, we have several shapes with the intrinsic symmetries. An intrinsic symmetry can be seen as an isometry between a shape and itself. So if I'm standing straight, my body has an extrinsic symmetry, but if I move my arms in a non-symmetrical way, then the symmetry is not extrinsic anymore, but intrinsically you still have it. So we are interested in this case when we are looking at intrinsic symmetries. So the problem that we are looking at is we are given a pair of shapes, and we want correspondences. Something like this. So the output of the method would be a map T that takes every point on my first shape M and outputs its corresponding point on the shape N. So, as I said, isometries preserve geodesic distance. First idea would be to put the geodesic error and minimize this. But this is a difficult problem. It's looking for, we are trying to look actually for a graph isomorphism. So only computing the geodesic distance is difficult, but minimizing this would be very difficult. So this is the general problem without talking about the symmetries. Now, when we have the symmetries, when you have a symmetry, nothing stops you from actually matching the left side to the right side, and conversely, right? So this means that we have at least two equally good solutions. So the problem is obviously not convex, and this is what we call a symmetry ambiguity in the shape matching problem. And it's not that bad if you match the entire left side to the entire right side. What is not nice is when you match only parts of the left side to parts of the right side, and conversely, because in this case you have a continuity issue in the solution. So, with respect to the initial question, it looks like the symmetry not only does not make the problem easier, actually it makes the problem. So the existing works, they start with some initial point correspondences, and then they try to propagate these correspondences in the neighborhood in a coarse-to-fine approach. But this is complex because we get into combinatorics, and it's error-prone. What we propose to do, it's a matching of shapes that have intrinsic symmetries, but without using these point correspondences. And this was a joint work with Max, Quentin, and Leo Gibas from Stanford, and was presented this year at SGP. The proposed method uses the functional map framework that was proposed by Max and colleagues for shape matching. And when we deal with symmetries, the intuitive idea is that we should match actually only half of the shapes and not the entire shape, because if my if my half of the shapes are identical, then you have a kind of redundancy, so you can just match half of the shapes, and then to return two equally good solutions. So this is the intuitive idea that we used. Just to remind briefly the functional map representation is that when you have you are given two shapes, a pointwise map T would take every point on the first shape and will shape. But when we talk about the functional map representation, we actually look at the space of functions defined on the first shape and the space of functions defined on the second shape, and we try to find a map between these two function spaces. It's important to say that this representation is complete in the sense that if you give me a pointwise map T, then we can compute easily the functional map representation. And conversely, if I have the functional map, then I can obtain a point-to-point map by using as function the delta function, and by transferring the delta functions between the two shapes. Okay, so how do we, in general, how do we compute the functional map? So remember that the functional map is a map between two vector spaces. And it's actually easy to prove that it's a linear map. So if we choose convenient bases on the for the two function spaces, then we can project the functions on these bases, and then the functional map admits a matrix representation, and we can easily write it like a simple linear equation. Then, if we are given enough pairs of functions on the two shapes, we can just solve a least square system and recover this functional map. And as function constraints on the two shapes, we can use different descriptors, like the hit kernel or wave kernel, or there is a regularization part also, but I'm skipping the technical details. So the functional map gives state-of-the-art results in isometric shape matching in general, for general shapes. But it still has the symmetry flipping that I mentioned earlier. So we still have the continuity issue. And the original functional map used some point correspondences to solve that issue. What we propose here is to avoid that. As I said, intuitively by matching only between half of the shapes, but we won't actually work at the point level on the half of the shapes. We will split the space of functions. And we will split the space of functions in a convenient manner for the given problem. We will split it into symmetric and antisymmetric functions. So the symmetric space will contain the functions that are invariant with respect to the symmetries. And then we have the antisymmetric space that is the complement. We have proven that, so sorry, I probably didn't mention that for the original functional map framework, we use Laplace-Beltrami eigenfunctions as the basis functions. So in this work, we have proven that there exists an orthogonal basis for the space of symmetric functions that is formed only by Laplace-Beltrami eigenfunctions. And the fact that this basis exists allows to two parts, into the symmetric part and the antisymmetric part. And these two parts can be estimated independently. So what we do is we will focus on the symmetric part. And there are at least two reasons to do this. Because we can also prove that whilst between two shapes, we can have multiple isometries. So each isometry will induce different functional representation. The symmetric parts of these functional representations will be the same. So the symmetric part is unique. And the second reason is that the function constraints that we use, like the hit kernel or wave kernel, are usually symmetric functions. So these functions, they carry information about this C+, about the symmetric part, and not about the full map. So what we will do is we compute the C+, and then we have some technical details on how to recover the actual point-to-point map and to report two equally good solutions. Okay, so what I explained before is when we actually know the symmetry on the two shapes, okay? And we can split the function space in the symmetric part and the antisymmetric part. But now a more practical scenario is when the symmetry is known on only one. It appears in practice. For example, I have the model of a human that is not deformed, and then I want to find the map between this undeformed person, for which I can easily compute the symmetry because it's extrinsic. And then I want to map this undeformed guy with a deformed guy. We can still do this. If we know the symmetry on one shape, we can still do this by projecting on the vector space that we know, and then we can transfer the symmetry and proceed as before to compute the point-to-point maps. Well, I'm not going into details, but I can answer to questions if you're interested. So. In this part, when you don't have the symmetry on one shape, you can transfer it actually. If you know it on one shape, you can transfer it on another shape, and this it's very interesting. So the method not only gives us a shape matching method, but it actually gives us also a symmetry estimation method, because I can, I'm transferring the symmetry on the other shape, and it's actually a very accurate symmetry that we get. And here we compared with state-of-the-art methods in symmetry, and we have actually better accuracy compared to that. And then for the matching, we also have better results. So, namely compared to the original map framework, we don't have the continuity problem anymore. We don't have the flipping between the two sides. So, to summarize this part on the 3D shapes, the question again was, is symmetry useful and is it used in 3D shape matching? And the answer is that apparently it seemed that the shape matching is more difficult when we have symmetry, but we have shown that we can factor out the symmetry and solve the problem as before. And as a bonus from our method, we get an accurate symmetry estimation on an unknown shape if we know the symmetry on one shape. And just to conclude, to put together the contributions that I presented, just to say that recently there have been large, we have increasing public repositories of images like Flickr or 3D shapes like the Google warehouse. And there has been an increasing interest for joint image and 3D shape analysis. And a possible application of the works that I presented is like to say, okay, I'm given a model of a deformed shape and an image. And I want to texture the model using the image. For the existing works on this, looks quite science fiction for now. But I think that we kind of have the pieces of the puzzle, but we have to put all this together. And how could we do this? By using another shape, by passing through another shape that is undeformed, by first doing a symmetry detection in the image with the method that we presented. And this will give us a clue about where the object is in the image. Then there are works on object deformation. And this would allow us to deform the undeformed guy so that it matches the image. And then we can do the texture mapping to the undeformed guy. And then with the method that I presented for the shape matching, we can do the matching between the undeformed and the deformed guy, and to transfer the symmetry and to transfer the texture. But there are some, we are looking at this application, but we are still missing some pieces in it. Okay. That would be all.
Okay, any question?
So what pieces are you missing?
What, sorry?
What pieces are you missing in this approach?
It's especially on the object deformation. I need to deform the undeformed cat so that it matches the image. This is not very clear. Well, there are generate automatically isometric deformations for a mesh, but then to optimize the matching between the deformed mesh, between the projection of the deformed mesh and the content of the image, it's a bit.
Okay, thanks.
So if you had eye tracking information on the images, would this be helpful? Like, for example, in Google Glasses, you might get information where people are looking at in the image.
It would be useful if we can prove that it would be useful because symmetries attract people's attention. So if you have a symmetric object, you will look at it. So this would be useful to localize the. It would be useful, let's say, especially in the cases where this is a nice case because I have the head of the cat and I can detect the symmetry with my method. But if you have a strong perspective effect and the data is actually missing, you can't do much with the symmetry detection. But we are very good at seeing symmetric things, even in a perspective, even from a perspective view. So that would help it would help for the localization part of the object.
Okay. Any last quick question? No. So let's thanks again.